Hi, Algebra 1. We're going to be working on Unit 5, Lesson 18 here, and we're going to be working on expressing our exponential functions in different ways. Here we go. These three expressions right here are all the same as 1.21 to the 100th power. In this first one, you're taking a power to a power right here, and when you do that, you multiply those exponents. So that's 1.21 to the 100th power. In our next one, 1.1 squared is this first part right here, and that is 1.21. And then that's being taken to the 100th power. And if we look at this one a different way, we could multiply those exponents, which gets you 1.1 to the 200th power, which means that this is also the same as 1.21 to the 100th power. One important piece here is that this is modeling the years since 1790. So in number 1, it's asking how many people were in the US in 1790. So that's going to be our starting point, which we see in the equation as 4,000. But if we go back, it's telling us that it's showing us the population in thousands. So this means it's 4,000,000, which means that I could add 3 more zeros onto the end for those 1,000 places, which is the same as 4 million. In 1860, I just need to recognize that that is 70 years since 1790, so my exponent is going to be 70 there. When I evaluate that, I get 33,897. Remember, this is in thousands, so I can really add 3 more place values there for those 1,000 places, so I'm at about 33,897,000. The approximate annual percent increase used in the model is going to be coming from our growth factor right there. We know it's growing because it's greater than 1, but after the decimal places, you're going to see the 0.031, which this is the part we need to get our percent increase, and that's going to be 3.1%. Remember, to find a percent from a decimal, we need to multiply it by 100, so that moves the decimal to the right twice. 2017 is 227 years after 1790, and when I evaluate that, I get about 4,000,000. Remember, this is in thousands, so I just need to add those 3 zeros on the end for those 1,000 places. So really, this is showing us we would have about 4 billion people in the U.S. in 2017, and no, that is not correct. At this point in time, we have about 600 some million people. So this model has not held true going way past 1790. In number 2, what percent increase does the model predict each decade? A decade is 10 years, so I plug that in there for my variable. And what we're really worried about here is not so much the total population, but just the percent increase. So I'm just worried about this part here. 1.031 to the 10th power is going to be about 1.36, which means that each decade or every 10 years, we're looking at a 36% increase in the population. And that 36% is coming from that 0.36 right there. Now we're going to write our equation in a different way. We're going to look at how can we include decades in this, so we don't have to calculate out hundreds of years, that we can just put in the number of decades. Well, every decade is 10 years, so instead of t here, I'm just going to put 10, and then we're going to raise that to the power of d, and d is going to represent the number of decades. Now this works because when you take a power to a power, you multiply those exponents. So for example, if we want to find the population 3 decades from now, I can just plug in 3 for there, for d, and when I take 10 to the 3rd power, that power to a power, we would multiply, that would be to the 30th power, which is the exact same thing as 30 years, which is 3 decades. Now, why would we go about this trouble to do this? Well, it's because we can reduce error. By just plugging in a number of decades, we're going to be plugging in smaller numbers, which makes it less likely for us to make mistakes. Here we're going to figure out what percent increase does the model predict each century. A century, cent is in there, which means 100, so it's 100 years. So I plugged in 100 here for our t for years, and to figure out what percent increase we're predicting, not the population, but the percent increase, we're just looking at that part with our growth factor. And 1.031 to the 100th power is going to be 21.18. So that's really, really big. We're not going to put that into a percent, but we're just going to understand that that means that the population would have increased over 21 times, or 21 times as large. In B, we're going to write our equation a different way. We're going to look at C representing the number of centuries since 1790. So if we wanted to look at, say, 200 years from now, that's just 2 centuries. And so if we write our equation like this, where we put in 100 for our years, all raised to the power of C, which is the number of centuries, we'll be able to more easily plug in a larger number of years because we're just plugging in how many centuries. So for example, if I wanted to see what the population was 2 centuries later, I could just plug in 2 for C. I'm taking a power to a power here, so we'd multiply that, and we would see that that would be the same as figuring it out 200 years from now. So it's the same thing, but just writing the equation differently can help us be able to plug in smaller numbers for our exponent. In our last problem, we have 3 expressions and 3 descriptions that we're going to match. In each case, $1,000 has been put into an interest-bearing bank account. No withdrawals or other deposits are made for 6 years, but they are going to earn interest every year. So our job is to match each expression with one of the descriptions, but it says that one group contains more than 2 expressions and one of the descriptions does not have a match. Before we get too far, I want us to just mark up one of these expressions to figure out what's happening here. So first, this 0.07 is showing us the interest rate. This would be a 7% interest rate. It's being added to 1 because it's going to be growing. The divided by 12 part comes from how often the interest is given. So basically, if they're saying you're going to earn 7% over the whole year, they're going to divide that by 12 and just give you part of that 7% each month. So in this case, the 12 is representing 12 months. And then the 72 is representing how many months since the account began. So 72 months is going up there. Our first account right here that we just marked up a little bit, that one is going to match with our second description where it is 7%, which we see right there, and it is compounded monthly. That means right here, monthly meaning 12 times throughout the year, once a month. The second expression right here is again showing 7% interest, and the 2 means 2 times per year. So the interest is given twice a year, which is also called semi-annually, meaning once every 6 months. The last equation down here, we have a power to a power, which means we can multiply those exponents. So this is really the same as being raised to the 72nd power, which if we notice, that's the exact same as the first equation, so it matches with that second description as well. We didn't have one that matched with the third description, so we're going to write our own equation for this one. And we have 7% interest. There's our 0.07 right there. 72 months, because it's going to be just like the other ones in there for 6 years. And then the part that we need to figure out is, it says that it's compounded every 2 months. If it's compounded every 2 months, that means 6 times per year. And so underneath our 0.07 in the denominator is going to be 6.